All right, so in the last video, we kind of, oh, there's hair on my pen. Oh my gosh. Okay, so in the last video, what we did was we were talking about, linearity in the inner product. And I sort of finished by saying, this proof here, if you can call it a proof, would still work if, this had some number in the front and, this had some number in the front. So I'm going to go ahead and just do it. And I know it's going to crowd this a little bit, but I think it'll be nice to see. So let's go ahead and put like a 2 in front of here and then a 3 in front of here, right? So what I'm saying is we're just defining our inner product a little bit differently. So it's no longer going to be a dot product, but it's going to be an inner product, right? So the inner product of A and B is going to be 2 times the first components multiplied plus 3 times the second components multiplied, right? I mean, this is just an example. So we still want to prove this property and we still want to prove this property. But so now our inner product is defined differently. It's not this, it's going to be 2 times this and 3 times this, right? And we can pull that all the way through and it's going to end up working here. So 2 here, 2 here, and 3 here, and a 3 here, 3 here, 3 here. It's a good thing I did this highlighting because it's easier to trace this. And then, so now the greens, so basically what this is I'm sure you can kind of see it, but this is AC, 2 times this first part and 3 times the second part, and boom, that's what we wanted, right? So this is exactly the same definition of the inner product. It's that for AC, and the same thing happened here for AB. And then you could do it with this as well, because again, if B was multiplied by 5, right, what this is, or A, for example, then that would just mean each component was multiplied by that scalar. So you'd have a 5 here and a 5 here. You could pull the 5 out and get that same thing, right? So what I'm trying to say is if you define your inner product by having some scalar multiple in front of your individuals of the component multiplication, you still get an inner product. Our properties still hold. And the beauty of this is that 2 and 3, you could write that as a vector, 2, 3. Whoops, my notation. So I don't know if that is resonating with you, but basically what that's saying is, you could define the inner product of A and B by including another inner product, another vector in here, right? So the space of all of these inner products is essentially equivalent to 2 by 2 space. Well, it's actually 2 by 4. We can get into that later, but the point I want to make right now is actually it's 2 by 2, 4 dimensions, 2 by 2. But the point I want to make now is this is a vector. So like, A, B, you could also throw a C and a D in there. And then so you'd have A1, B1, C1, D1 plus A2, B2, C2, D2, right? This is the same thing here, right? You've got A and B, but this 2 and this 3 you could kind of encapsulate in this C and the D, because we could have done this same proof if this was 4 and 5, or honestly if it was a variable, or if it was 2 variables, right? So if in this proof, honestly that might be kind of a cool thing to do, is say, here we have this, but let's focus on A and B and see if basically what we're seeing is these properties hold on A and B. So I'm actually going to go ahead and do that real quick. I feel like I'm going down a rabbit hole and might confuse people, but let's do it. So if we define our inner product of A and B as this, right, as this thing that we had here, right, is equal to A1, B1, C1, D1 plus A2, B2, C2, D2, right? Now what we're seeing is, do these linearity properties hold? Do these linearity properties hold, this one and this one, if our inner product is defined by this? And the answer is yes, because you could just treat C and D as you treated 2 and 3. So they're going to follow along here, and they're going to pop out here at the end. So what that's actually saying is, this inner product is actually linear in A and B, A, B, C. It's linear in all of these things just because of this property that if you multiply these components by some scalar, the linearity remains. Now, and so that's kind of all I really want to say. But there's really one extra part is if these were complex numbers instead of reals, and this was a complex and this was a complex, which 2 and 3 are actually complex, but they're also reals. So I'm saying if we had something more general here and here, these inner product properties are a little bit different for complex, but they would still hold, right? The only reason I hesitate and I'm talking about reals instead of complex is because there's one thing I don't know, because if you have, let's do this, so if you have A, I think it's easier to do it as like U and V because these are complex. This is the same thing as U, V kind of, right? So what's weird is, in the complex case, there's really only two things, right? There's one that you leave the same and a second that you use as the conjugate. But I don't really know how to do that. Like, I don't know how you would just do like this, for example, right? Because, you'd probably conjugate the second one, leave the first one, but I don't know what you would do with the third. I always like to emphasize that the reals is just a specific case of the complex. And I'm like, well, I don't really know how to do it in the complex, but I did know how to do it here. And the reason we know how to do it here is because it doesn't matter, like the bars don't matter. Because the complex conjugate of a real number is just itself, right? So that's why this question of like, I don't really know what to do, that's why it doesn't apply here, is because there are no conjugates to take. Because, in the complex plane, right, if you have a number like this is a complex number, the conjugate is here. But if you have just a real number, its conjugate is itself, so you have nothing to really worry about. So this multilinearity stuff, with the complex case, I don't really know exactly how to do it. So maybe someone else does. Maybe they'll leave a comment. So yeah, that's all. Thanks.